Hi, my name is Ryan Turner. I'm a PhD student at Swinburne University of Technology in Melbourne, Australia, and the talk that I prepared for Cosmology from Home this year is titled Testing the Cosmological Model Using the Growth Rate of Structure in the Local Universe. I'll be discussing why we want to know about the growth rate, how we can measure it using peculiar velocities and correlation functions, and how this method, combined with current and future data sets, will enable us to perform precise tests of the standard cosmological model. And so I'll start with a brief introduction. The abundance of data available to us due to the various surveys and missions of the last 20 or 30 years or so means that we now have a detailed understanding of the history of our universe, from the very first primordial fluctuations all the way up to the present day. One of the revelations of this is the notion that the rate of cosmic expansion is accelerating, what we know as dark energy. Until now, we've chosen to view this dark energy through the lens of a cosmological constant called lambda, and this forms an integral part of our standard cosmological model. However, lambda is purely phenomenological. It has no physical justification for being in the standard model, but when we include it, we find that the model gives us good predictions for our observations. This still inevitably leads to people giving alternative explanations that try to provide some physical meaning to the acceleration that we see, whether that be through modifications to general relativity or through the actions of a fifth force. And so we can test the standard model to look for the effects of these physics by measuring the expansion history of the universe or the growth rate of structure. We can measure the expansion history of the universe either by measuring standard rulers, such as baryon acoustic oscillations, or standardizable candles, such as type 1a supernovae light curves. And we can measure the expansion history with about 1% accuracy. We measure the growth rate of structure from the initial perturbations in the matter density field as a function of redshift, or as a function of scale in redshift space. And we can measure the growth of them via the clustering of galaxies, or through weak lensing, or by using peculiar velocities. However, our measurements of the growth of structure have errors which are about an order of magnitude larger than those from the expansion history of the universe. And so what we want to do is we want to make the best measurement possible of the local growth rate by producing an optimal combination of peculiar velocity and galaxy clustering statistics. And so what are peculiar velocities then? If we were to view the universe on very large scales, we'd see that space is expanding smoothly. It is determined by the Hubble-Lemaitre law, and all of the galaxies within it are moving according to that flow, shown by this green line here. However, as we zoom in, we see that galaxies are gravitationally influenced by the inhomogeneities in the matter distribution, and this imparts a deviation to this smooth expansion, and we term this as the galaxy's peculiar velocity. What this means is that the redshift that we measure for an object, its z observed, is not the true redshift of the galaxy, as it has this peculiar velocity component modifying it. And so what we require is a redshift-independent distance indicator for the cosmological or true redshift of the object. And with that, we can break this degeneracy between z cos and v pec and recover the peculiar velocity. Because these velocities are imparted over cosmic time under the gravitational influence of large-scale structure, that means that it probes fluctuations of gravitational physics that link motion to the underlying matter distribution on the largest scales. And we can parameterize this as the combined parameter f sigma 8, where f is the growth rate of structure and sigma 8 is the amplitude of the linear power spectrum in spheres of radius 8 megaparsecs on the H scales. So different theories of gravity predict different behaviors of this combined parameter f sigma 8. And modified gravity effects are observed in fluctuations on the very largest scales, where peculiar velocities are an unparalleled probe of cosmology. And so by precisely constraining measurements of f sigma 8, we are able to distinguish between these theories. And one way of extracting information from peculiar velocities is via the correlation functions. The first correlation function that I'll touch on is the galaxy-galaxy correlation, or 2-point autocorrelation function. And we can think of this as being the excess probability of finding two galaxies separated by some distance r, or the tendency of galaxies at any given separation to cluster under the influence of gravity. On the right hand side here, I'm showing a typical galaxy pair A and B in relation to some observer O, and the geometry associated with all these things, where this R vector here, this separation is the same as this R vector here. And so if we have a survey of galaxies, we can measure this R value for every pair of galaxies in that survey, and by taking the average measure of these correlations, we get an estimate of the galaxy-galaxy autocorrelation function. The second correlation function that I'd like to talk about is the velocity-velocity autocorrelation function. We expect the velocities of galaxies to be correlated in some way due to the force of gravity that acts on them. So we expect galaxy velocities to be directed inwards towards overdensities, such as clusters, and to be directed outwards away from underdensities, such as voids. Like before, if we have a survey of galaxies and we can take any pair A and B, we can measure the correlation between the velocities VA and VB, and by taking that average measure, we will get an estimate of the correlation function. We cannot measure these galaxies in 3D though, we can only measure the radial components, and so what we measure is psi1 and psi2, which are estimators that characterize the correlation between the radial velocities in the both perpendicular and parallel directions in regards to the line of sight. The main correlation function that I wish to discuss though is the galaxy velocity cross-correlation function. So now what we are doing is correlating velocities with overdensities, or galaxies in this case. And we expect that by increasing the matter over density of the point, that this will pull galaxies towards it under the influence of gravity. In this figure, we are showing two separate cases, one where an overdensity is in between an observer and a velocity, and one where the velocity is in between an observer and an overdensity. In the top case, this velocity is being pulled towards the overdensity, and so this velocity is decreasing along the line of sight with respect to this observer. And so we are seeing a negative peculiar velocity, and so we find negative correlation. As this overdensity increases, we'll find that this velocity decreases. The bottom panel shows the opposite case. So this velocity is increasing along the line of sight towards this overdensity, and so as this overdensity gets larger, we expect this velocity to also get larger, and so we find positive correlation in this case. And so if we do the same as we did before and take the average infall across all pairs A and B in our survey, we get a measure of this galaxy velocity cross-correlation from the average infall. The survey data that we use to measure these correlation functions comes from the 6-degree field galaxy survey. These data were taken on the UK Schmidt telescope and using the 6DF spectrograph, and consists of two samples, a redshift survey, 60FGSZ, containing over 125,000 galaxies, and a velocity survey, 60FGSV, containing nearly 9,000 galaxies. It covers 41% of the total sky, all in the southern hemisphere above a galactic latitude of 10 degrees, out to a median redshift of 0.053. When we work with real data, there are some issues to take into account, things like varying completeness across the sky, patchy observations, dust extinction, things along these kinds of lines. But the one that I want to talk about, and one that can be used to aid our measurement, is redshift-space distortions. Redshift-space distortions present another source of growth information that we can use. In this approach, we measure redshift-space distortions in the clustering distribution of galaxies in redshift space. So what we do now is we use positions based on our observed redshift in order to measure our peculiar velocity, rather than using the cosmological redshift that we would otherwise infer from redshift-independent distance indicators. Redshift-space distortions have the effect of amplifying overdensities, as we can see on this part of the cartoon, as well as imparting a dependence on mu, which we call the angle to the line of sight. I've added a vector mu on this figure, and I've chosen it such that it entirely bisects this angle theta AB, so the angle mu RA and the angle mu RB are equal to one another. We can also relate the density in real space, delta R, and the density in redshift space, delta S, by this equation in the bottom right here, where the redshift density is equal to the real density multiplied by this factor of 1 plus f times mu squared. Following the blue equation, linear RSD theory is able to measure f sigma rate and b sigma rate, where b is the linear galaxy bias. And this is shown in these three equations, where the top one relates to the galaxy-galaxy autocorrelation function, the second to the galaxy velocity cross-correlation function, and the third to the velocity-velocity autocorrelation function. In the plot that I'm showing on the right, that I've taken from Peacock et al. 2001, they show the redshift space 2-point correlation function from 2D FGS, And on this plot we can see two different forms of RSD effect, along the line of sight and across the line of sight. We can capture this cosmological information that's contained in RSD via the multipole moments, both of the galaxy-galaxy autocorrelation function on the left and the galaxy velocity cross-correlation function here in the middle. If we take these equations in tandem with psi parallel and psi perpendicular, which are the radial and transverse correlation functions of the 3D peculiar velocity field, then we have an ensemble of models with which we can start to do science. In this slide, I'm showing some of our results that I've taken from a paper of ours that was recently submitted. So we're using our ensemble of models, we estimate the best fitting values of F sigma rate and B sigma rate using a chi-squared minimization procedure. In the plot on the left, I'm showing the 5 models that we use in that ensemble, plotted against distance s. Our models are shown in black, and our estimate of those models is shown in red. From top to bottom, we have psi1, the velocity-velocity estimator. We have the monopole of the galaxy-galaxy autocorrelation function. We have the dipole of the galaxy-velocity cross-correlation function. We have psi2, the other velocity-velocity autocorrelation function estimator. And we have the quadrupole of the galaxy-galaxy autocorrelation function. This right column shows our results when applied to 660 FGS MOCs, and so we show here the MOC mean of those. On the left, we show our results when applied to the two 60 FGS data samples, the velocity and redshift sample, and the error bars shown in both plots are the standard deviation across the 660 FGS MOCs. And in the plot on the right, I'm showing our posteriors for F sigma rate, for B sigma 8, and for a third parameter sigma v. This is the nonlinear velocity dispersion, and it is required for our chi-squared fit. We do this for the two 60 FGS data samples, the velocity and redshift sample, and these contours represent 68 and 95% confidence intervals. We fit in the range 27 to 123 megaparsecs on little h, and we do this for 3 different combinations of our 5 models. The blue contours represent our fit to the two galaxy-galaxy autocorrelation function multipoles. The yellow contours represent our fit to the velocity-velocity autocorrelation function estimators and the galaxy-velocity cross-correlation function dipole, and the red contours represent our fit to all 5 models. We can see from the yellow contours that our fit to the velocity data is very roughly constrained and provides very little info in terms of B. Our blue contours perform better, but when we look at our fit to all 5 models, we see that we get the tightest constraints of all 3 combinations. The weakness of the constraints obtained from the yellow contours indicates the improvement that this analysis would see if we were to have access to better, more accurate velocity measurements. Focusing now on our F sigma 8 result, we compare our measurement with other measurements from the recent literature that span different datasets and different methodologies. In red, I'm showing measurements obtained from 60 FGS data. In blue, I'm showing measurements obtained from non-60 FGS data, and in green, I'm showing measurements obtained from velocity density field reconstruction techniques, and we find that our result in black is consistent with all of these. Our method uses an optimal FKP weighting, which reduces the effect of random noise at small scales. It is self-consistent in terms of the covariance between the statistics that we use, and our method is also ideal for being scaled up with future, larger surveys. Circling back now, the expansion history has been measured with around 1% accuracy, but what about the growth rate of structure? In our previous paper from 2021, we tested galaxy and velocity cross-correlations on the LPicola suite of simulations, and found that we could measure the growth rate with around 15% error, although we did ignore the effect of RSD for that work. Recent forecasts from Coda et al. And Howlett et al. Have predicted that by combining future redshift and peculiar velocity surveys, also labelled 2 field in this plot from Coda et al. On the right, that they can produce measurements of the growth rate with around 3% measurement error. There are 2 important surveys on the horizon, and these are the DESI Peculiar Velocity Survey and the Foremost Hemisphere Survey. By taking these 2 together, they will cover around 34,000 square degrees of the sky out to the redshift limit at which the fundamental plane is no longer useful, and they will measure combined a total of around 650,000 velocities. With data like this, it is feasible that in the next 10 years, we will be able to measure the growth rate with around 2% error. And with a measurement as accurate as that, it is possible that we'll be able to discern between different cosmological models very accurately. To summarise, we can combine the effects of RSD with the galaxy velocity cross-correlation function in order to constrain the growth rate of structure. and this information is captured in the multipole moments of the correlation functions. By combining these sources of information together, we produce tighter constraints than if we only considered RSD, and this is shown in our fits. So by fitting to all 5 models, we produce smaller contours than if we fit to only the galaxy-galaxy autocorrelation function multipoles. Our method produces results that are in agreement with those from the recent literature, and these other results are obtained from various datasets and use different methodologies. Our method can also easily be scaled up for use on larger future surveys, such as the DESI Peculiar Velocity Survey or the Foremost Hemisphere Survey. By taking these 2 surveys together, they will measure on the order of 650,000 velocities, and will be able to measure the growth rate with around 2% uncertainty. With a measurement of growth this accurate, it will be possible to start distinguishing between different proposed cosmological models. Thank you for watching my video, and I look forward to discussing everything else with you at Cosmology from Home.